And thank you for sticking around. It's the last session, and probably we are all a bit tired. So expect a bit of colorful fluid dynamics to cheer you up. And this is a talk about WaterLily, and WaterLily is a CFD solver for incompressible fluid flow that can do very cool simulations with moving objects and can run in different backends. So I will explain you how we do all of that. So just some background for people who's not very familiar with computational fluid dynamics. So we basically solve the Navier-Stokes equation, here the incompressible form, and you can see that there is a RE number here. This is the Reynolds number, and the problem we have with CFD is that for high Reynolds number, we have a very wide range of spatial and temporal scales that we need to solve, which means very expensive simulations. Here you can see one of these simulations of flow past squared cube, and well, all the scales that needs to be resolved in space and time are super, super expensive. So this is where HPC comes into place, and it's very important for CFD. So I don't need to convince you probably that doing Julia for CFD is a good idea, but I will just summarize it here. So first of all, of course, CFD needs to be fast because otherwise it's super slow to run all these, simulate all these temporal and spatial scales. So it needs to be compiled language. So that's a check for Julia. We also need the language to have parallelization capabilities. And in Julia, we can do that at the shared memory level and in the distributed memory level as well with the different packages, which is also very, very important for CFD. So that's another check. And then we only need to run in the different architectures that are out there and that needs to, like, they keep coming out, and we need to be ready for those architectures. So again, thanks for the Julia community that's been working a lot on this. We have all these amazing packages that allows us to do that from a very high level point of view. So yeah, that's another check, and this makes Julia really ready to simulate CFD. Then on the other hand, we have added benefits to this, and of course, this is the solution of the two-language problem. Here we can integrate CFD solvers with machine learning libraries very easily. I've suffered this pain with other Fortran and C++ solvers in the past, and honestly, this makes it so much better, so I really appreciate this. And of course, the active community, like we are here in JuliaCon. I've learned a lot from other people, all the new developments, like engaging with core developers. It's super useful, and so that's very important as well. So let's talk a bit about WaterLily. So as I mentioned, we simulate incompressible fluid flow, and we do it in a finite volume numerical method. So we basically, our cells contain pressure and velocity information in a staggered manner, so we conserve mass locally. This is typical in finite volume methods. And we have an inverse boundary method to represent the solid interface of the problem. So here you can see there is a fluid domain and a solid domain, and then we have this interface that kind of smooths the solution from one to another. And this is the boundary data immersion method, which in short, what we need to do is to define a sign distance function, and then with that, and using the derivative of this sign distance function, which we can do with AD, we can compute the body normal, the curvature, and the velocity of the body, and then interpolate the effect of this boundary into the flow solution. This, what allows us really is to have very arbitrary prescribed motions of bodies that are shrinking, moving in whatever manner you want them to move. So we can do simulations which would be quite tricky when you need to do them in a body-fitted grid. So here, actually, we have a Cartesian grid that embeds this solid boundary. So the boundary can move freely, and we just take into the effect of the solid boundary through interpolation into the fluid. And a bit more about the numerical methods in WaterLily. So we have a geometric multigrid because in this Cartesian grid, it's very easy to implement this to solve the pressure Poisson equation. And we have a projection method to do the time integration for the divergence-free constraint of the problem. So this is just a short recap of the numerical methods. And now I want to talk a bit more about how is the setup done in WaterLily. So we have, let's say, three main containers. Here is a simulation that holds information about the fluid, which is another struct, and the body. And what we do is that by defining the size of the problem the initial condition for the fluid, and the geometry of the solid boundary, if there is any solid boundary, then we have all our setup completed. For additionally, we can also run on the different backends, just changing a flag, let's say, as the previous two talks. So I think this is where this is going a bit for the users. It's very convenient to have just a single parameter that they can say offload to GPUs or just run in CPU multi-threaded or whatnot. So we have the same with the same setup with the memory keyword argument. And as you can see here, with just these very few lines, we set up this Taylor-Green vortex test case. This test case is just normally used for validation and benchmarking of CFD solvers. So you will be seeing some results about this. And you can see that we have this function, u lambda, that just sets the initial condition. Here is just some harmonic function for the velocity field. And then it returns a simulation with the resolution 2 to the power of whatever number we want. And then we can just time step this simulation object. And the time stepping just produces this evolution of the flow field. So as promised, we can do other geometries. Here is a donut. And the only thing we need to do to set up this test case is these very few lines of code. So we define where's the center of the donut. We define the outer and the inner radius. And then we just need to define the actual sign distance function through this body code block that you see here. And with only these very few lines, we have a geometry defined within our domain. Again, this returns a simulation object that we have a method for doing time stepping of the flow. And okay, we can do moving objects as promised. This is like an arbitrary jellyfish, I call it. So it's just a hollow sphere that intersects a plane that moves in a sinusoidal form and just shrinks and expands. To set up the simulation, it's just these very few lines of code. And what you need to do here is just to be a bit clever about the sign distance function, but also know that we can define different bodies. Here we call it autobody. And these have operations. These have an intersection operation with the minus sign between the sphere and the plane. So you create a new autobody that is the object that we pass to the simulation. And with just these very few lines of code and another call for doing the time stepping, we can run this simulation very easily. So let's look a bit about what are we doing behind the scenes to have this flexibility, right? So here is an example of how to compute the divergence or in a cell of our grid. It's very easy. It's just in finite volumes with Cartesian grids. It just looks like what comes in and what comes out of the cell, and this hopefully should be 0. When we want to implement something like this, the first thing we do, or we did actually before porting our code, was to define a macro that we call loop, that basically abstracts the loops whenever we need to use them. So instead of writing explicit loops, we just use this macro. And here, okay, it's not very useful for just one loop. You could just write it, and it would be doing the same thing as you can see here. But for example, if you want to pass some performance decorators to these loops or to running multi-threading, we were doing like just changing this macro. We would accelerate all the loops of our code. So that was pretty useful for us. Well, I haven't mentioned, but here for this divergence operator, we have a couple of helper functions. This partial delta, this just says, when I am in this Cartesian index, I look at the direction small capital I, and then go one step behind and one forward and see the difference. And we do this for the different dimensions of the problem. So you can see here also that this is multidimensional because we operate with Cartesian indices. So writing like a 2D flow solver or a 3D flow solver is the same. We don't modify our algorithms. So we did this abstraction, which maybe was out of laziness because we didn't want to code all these repetitive loops all the time. But it also gave us an advantage, which means that the computational load of our solver was now contained in this very small code base, this loop macro. So when we wanted to port this to GPUs, it was very easy to do this with kernel abstractions that were kind of an adaptation to this macro loop. So this is an adapted macro loop that generates kernels based on kernels abstractions.jl and calls these kernels. So we have here, again, a couple of utility functions for the macro processing, like grab and setDiff, just operates on the symbols of an expression. And this passes all the arguments to a kernel that is automatically generated in every loop in our code. And then we call this, as you can see here, with a specific backend. This backend is related to the user keyword argument memory that could be specified for array or QArrays or rock arrays, right? So because kernel abstraction supports this. And to be fair, we did this porting of our CFD solver just in a couple of weeks or 3 weeks. And it was very easy. I did not have much experience on GPU programming before, honestly. And it's really, really amazing that we have all these packages such as CUDA.jl, kernel abstractions, and whatnot that we can, like, it allows us to port a code that would be quite tiresome in some other languages in a very easy fashion. And just with this, literally almost this change, we were able to run on GPUs all of a sudden. And as we will see later, this gave us a huge speedups. And well, guess what? Our code base went from 1,000 lines of code to 1,000 lines of code, more or less, because these were more or less the added lines in the code from the adaptation from one macro to the other one. So it's pretty amazing. You can see this is a very minimal CFD solver in terms of code base. So it's easy to, let's say, engage with us, contribute to the solver, and we always appreciate those. So let's look at some different test cases. We will be looking at validation, benchmarking, and profiling. Again, we'll be looking at the Taylor green vortex, as I've presented before, but also the sphere and a moving cylinder. And we will be seeing how the solver does on these different cases with increasing complexity from no body to a moving body in the flow. So first, validation of the Taylor green vortex. Here we are looking at the evolution of the kinetic energy and the evolution of the dissipation, or also the rotational energy of the fluid, if you want, for different resolutions of the problem. Here we go from 64 cube grid cells to 112 cube grid cells. And we can see that we are increasingly matching the reference, direct numerical simulation data, showing that our solver correctly solves the Navier-Stokes equation. This is the expected result. And actually, this fine resolution is the same as the DNS one, and we are matching it very well. So just to show that this is just not to, this is actually solving Navier-Stokes in the background. So it's doing the job. And then we tested a bit on the benchmarking side. What's the speed up we get when we run in multi-threaded CPU or in a single GPU compared to the serial execution. Here I'm showing for the Taylor green vortex on the left and the cylinder on the right, because the sphere is very similar to the Taylor green vortex because the body is fixed. And you can see that we have speedups, which are the small numbers that you see on top of the bars, up to 8 times as faster for the 16 multi-threaded. So we are not hitting 16 when we have a 16 multi-threaded CPU backend. Maybe it's a bit our fault, maybe it's a bit kernel abstractions. I talked to Valentin, we will need to debug that a bit. But we are pretty happy with that. And then for the GPUs, this was tested on H100 in Mare Nostrum 5. We are very, very fast when we are filling up the GPU. And the speed that we get when filling up the GPU here on the bottom axis is actually the degrees of freedom of the problem, or the number of cells. So this is in millions. So for the moving cylinder, we go up to 300 million cells we can fit in a single GPU, which only consumes, like, for this single precision, like 39 gigabytes of memory. So we have a pretty good footprint, I think. And the speeds we get are, like, for the Taylor green vortex up to 200 times or 155 for the moving cylinder. So that minimal change we did in the macro allowed us to get these crazy speedups, which is pretty good. Okay, let's talk a bit more about the cost. So cost in CFD solvers is measured as the time that it takes to solve the Navier-Stokes equation per degree of freedom of the problem per time step, right? This is a way to compare, like, I am faster or slower than other CFD codes, and so on. It depends a bit on the numerical method behind the scenes. So we have a finite volume, which is a low order scheme, but people that uses, for example, Trixie, that use the DG, or people using flux reconstruction or other high order methods, they have a more costly, by definition, by the numerical method, because it needs more operations, a more costly algorithm, but in a rough manner, we can compare to other CFD solvers. And you can see here, for the different grid levels that we tested before, and the different free cases, how does this cost evolve? So as we are filling up the GPU, our cost decreases quite a lot, from about 11 nanoseconds to here the lower one is 1.44 nanoseconds. This is in par or actually better than other CFD solvers that are well established, like, I don't know if you know them, but NECRS or SOT2D. These are like Fortran CUDA solver, a Fortran with OpenACC solver, other C++ solvers we have other benchmarked against. Like, we are at least as fast. So Julia can be very, very fast. And this is a way that we can show it. Of course, we did also a bit more of profiling. So here you see the time that it takes for one time step on the different kernels of our code. So you can see the kernels on the right. Basically, we have scale U is just like a scalar operation on the fluid velocity, like a broadcasting. It's a very cheap one. You don't even see it. Here we have the big one. Project is the pressure Poisson solver. It's just a solver, like we need to do a solver of the Poisson equation, and this is the most expensive part of our solver in all of the cases. It's very expensive because here the test, as you can see, is just single precision on my laptop GPU actually, and the problem of these linear solvers is that the reductions, I think, they are quite expensive, and we've not optimized those yet. So for us, this takes a lot of time, but this bottleneck is now identified, and we can target it to improve the algorithm. As you can see, adding the moving boundaries or a boundary or a moving boundaries for this cylinder, we increase the boundary condition cost. It's much more than I was expecting when I did the profiling. So definitely we need to try to tune that one as well. And on the other hand, like when we actually compute Navier-Stokes equation, this convective term and diffusive term through this kernel, the comp_diff, this is like let's say a pointwise kernel almost that only looks at these steps in the Cartesian index, like in the array through Cartesian indices. This is very, very cheap on the GPU. Like, you cannot even see this kernel almost here. So yeah, the bottlenecks are basically on the reductions on the GPU, I think. Okay, so quick recap. WaterLily is this very minimal code-based CFD solver for incompressible fluid flows. You can do crazy geometries, moving, deforming, whatever you like. You can run in this single flag. You can do serial, multi-threaded, and single GPU. We have very competitive cost, and well, actually in the presentation, maybe in the title, you saw that we had like it's a differentiable solver. Well, we got that actually a couple of weeks ago because we need to fix some functions about the types. But it works very well on the CPU backend, and we are now fiddling with the GPU because it was not working out of the box. Also, we were using forward diff, and we need to switch to enzyme more probably because it's now supported or will be supported by kernel abstractions on GPU. So that's our way forward. I've mentioned some of this. Then for those who know a bit about CFD, you may have realized that we have a constant resolution everywhere in the domain. Actually, close to the boundaries, normally the flow has very tiny scales. So this means that if we need to resolve those, that same resolution is applied everywhere. This is super expensive, of course. So if you need to do like turbulent boundary layers and so on, it's very, very expensive. So there are a couple of ways to fix this. One is to have a formulation that allows you to have a very fitted or confined domain close to the body, which still produces like a physical solution. And this is through the Biot-Savart boundary condition, which basically is a prediction of the velocity on the ghost points of our domain, which is much better than the typical predictions that you do when you just do a convective outlet, for example. This is a work in progress that will be published soon. Then we also have plans for a volume of fluid method, so we can do multi-phase flows, and just some grid stretching, so we can fit these cells close to the boundaries as we need for turbulent boundary layers. And that's all. Here you have the QR codes for WaterLily or for these slides if you want them. And yeah, just enjoy the colorful fluid dynamics, I guess. Thank you.
Yeah, thank you very much. We have time for one quick question, maybe.
Yeah, thanks, Bernat. A very nice talk. Because you showed so many nice performance measurements, I wanted to ask, did you already try Julia 1.11 with your code? And did you see any performance regressions like we did?
No, I haven't. Okay, use this, sorry. I haven't tried yet because the benchmarks were in Mare Nostrum 5 and they have 1.10.4. Actually, that's on the CPU part of the cluster. On the accelerated part, they have 1.10.2, and that's the version that you saw here. I definitely need to test for 1.11, and I have a benchmark suite that very easily can run several Julia versions through Julia app, and you can check regressions or speedups. So that's definitely something I want to look at.
All right, thank you.